Okay, so good afternoon, everyone. We will continue with where we left last time, and this is where we left last time. We were discussing SVM, and yeah, so we did all this, and yeah, so we said that what are the forms of the supporting hyperplane, and they look like this, and then we derived the optimization model, which is to minimize the gap, okay, or in other words, to minimize the margin, maximize the margin, and and this is the margin, and then if we reverse this and take the square, then it's the same thing as minimizing this quantity. And then we also saw that there are constraints, because this data must lie on this side of the hyperplane, and this red data must lie on this side of the hyperplane. So these two inequalities must be additionally satisfied. So this, if we combine these two, then this is the combined form of the inequality. And this is the optimization problem that we are supposed to solve. And this is the prediction. Okay, once you have found the optimal W, then optimal W and B, then you can solve, you can like predict, okay, for a given X, you can now start predicting. So, and then, so this is the optimization model we have. And so this problem, this is a primal problem in standard form. So this is in the standard form we have written. We have multiplied by the minus on both sides. So inequality we put in standard form. So this is the standard form of the inequality. And then this is the primal problem in standard form. And we notice that it's a convex quadratic programming, and with where objective is quadratic, obviously, and then the constraints are linear. This is a linear constraint. The problem can be recast also in the dual form that we always can do. For a primal problem, we can write a dual form. So for that, we write the Lagrangian, which is this, and then the dual function for this is the infimum of the Lagrangian. And we know that this is a convex in, so the Lagrangian is convex in like WB, and then we can find the minima of the L by the first order condition. So we equate this to 0, gradient equated to 0, and we solve for W and B. So if we do that, so we take a derivative with respect to B and with respect to W, and this is the W we get, and we substitute this in the Lagrangian, the W value that we obtained. And this is what, after substituting, we get. So in other words, we have infimized over W and B. Okay, so in our case, this WB acts like the X variable that we have been talking about so far. Okay, so here, like, you should not get confused what is X and what is W, right? Because here the problem is formulated in terms of X and B. Okay, so these are the things you're supposed to minimize. Okay, so these are the unknowns in this case. Okay, so if we infimize this over that, then we will get this. First order condition is this, and then this is what we have found here, and we have substituted W there. Okay, and yeah, so this is the dual function that we got after substituting the W. Yeah. So lambda I yi being 0 was used here. Okay, so lambda I yi being 0 was used, must have been used somewhere here. Yeah, so g of lambda will be this. So this is after simplification, and xi and then we have xj. Okay, so the w we have to substitute here. Okay, so if we substitute w, then okay, so this term let's see. Yeah, so let's see how it so w we have to substitute here. So yeah, it is a norm of w square, and w will be substituted here also. So here we can see yj, and then yeah, here it's written in terms of j, but yeah, so if we substitute w here, then we will see these terms like lambda I, yj, yi. So yi is here, yj is coming from here, and then xj dot xi. So xi is here, xj is here. So those will be here. And if we substitute it here, what do we get? Yeah, so this is norm of w squared. To norm of w squared, then we will have xj dot xj terms, right? And this term is sum of lambda is coming from here. It seems that the w is going to be 0. Why is that? Norm of w squared. That's not very clear, is it? Is it? Yeah, so here, yeah, so these are the conditions given to us. So sum of lambda I, yi is 0. And what would be the norm of w then? And we also see a half here, right? So half of norm of w squared, right? So this is half of w transpose w. So what will happen if we do this? Half of w transpose is this guy. So this will be summation of lambda j yj xj transpose of summation of lambda j yj xj. Okay, so this will be what, right? So here j is equal to 1 to m. Okay, so what do we get from here? So we have these terms to be multiplied, and we have lambda I, lambda j terms are there. Okay, it's better to put I here, right? Because they will get mixed also now. So it's good to identify which one is coming from first sum, which one is coming from second sum. So if we mix things up, what we will get is actually the same guy, but and there is one of the term here and half minus one of these terms is here. Okay, so that's why we will get 1 minus half here. Okay, so this term, okay, this term will be half of lambda I, lambda j, yi, yj xi, okay, dot, sometimes we also write like this, xi xj, and I equal 1 to m, right? So this is this part, and if we now try to see what is this part, then this part will be the same term. So this will be again, so this will be like minus of this, okay? So minus of lambda I, lambda j, yi, yj, xi dot xj, okay? So one of the term will be that, and and then what are the other terms here, right? So one of the term is lambda I, sum of lambda I, so plus sum of lambda I, and another term is lambda I with b, okay? So plus sum of lambda I, and yi is also with b, right? So yi, okay, and I equal 1 to m, okay? So this term, if you see, and this term, if you see, they are same, but it's just that this is half, and this is, so the total will be minus half, okay? If you add these terms now, so you will be left with minus half, which is this term. Sum of lambda I is there, which is here, and this term will go to 0 because sum of lambda I yi is 0, okay? So b is a constant, it can come out. So this will be sum of lambda I yi, that will be 0. So what you're left with is this guy, and this half of this and minus 1 of this will be minus half of this guy left here, okay? So that's how we get this. Now let us move ahead. So the dual problem now can be written as, in the dual we do the maximize, right? So this is our dual function, and we are trying to maximize this, and we always know that lambda is greater than or equal to 0, and we additionally have this condition now, which tells us that lambda I yi is equal to 0. Okay, so this is the SVM dual problem. Okay, so we can also solve this instead of solving the primal. Okay, so this was our primal problem, and this is our dual problem. In the primal problem, the variables are w1, w2, wn, like these are the components of the vector w. N is the number of features, so number of features, and primal is convex as well. Okay, so it's convex because we have a quadratic objective, so it's a convex because this is of the form half of w transpose identity times w, and this, remember, this was a P matrix, and this is identity is positive definite. So that's a convex, we know that, and this is a inequality constraint, linear constraint, right? So when we have that, then we know that this is a convex because this function is linear, so this is convex. So the constraint functions are convex. Constraint plus objective function are convex. That's the definition of convex optimization problem, right? There is no equality constraint here, obviously. Now, if you look into the dual has the variables. The variables are lambda 1 to lambda m. Now, this is the important point I was telling you, right? Which one to choose depends on n and m here. Okay, so if you prefer, if m was small, if m turned out to be small, then you may prefer to use, for memory savings, you may use dual. Okay, because you will apply some solver that needs smaller dimension. And if n is smaller, then you may go ahead with primal to save the memory. So here m is the number of data samples, and dual is convex. Yeah, so dual is also convex. Well, it's the objective is convex, and then the constraints are also convex. Okay, so again, this turns out to be convex, and these are convex as well. Okay, so we, I mean, dual function is always convex anyway. I mean, convex in the sense like it's a concave basically, but I take a negative of that and it becomes convex. Okay, in that sense, I call it convex. Okay, because I can change it to convex. Okay, so it is more precisely G is a concave, but then I will make it convex by doing a minus of this. So you can verify, because we have already proved that the dual is concave always. So the negative of a concave is always convex. Okay, so this can be changed to minimize negative of the objective. Okay, so negative of the objective, which is this guy here, and equality constraint functions are convex. So overall, it's a convex function. Okay, this is minus lambda I less than equal to 0 in standard form, and this is a linear. So linear is both concave and convex. In this, for our purpose, is convex. These functions are convex, and negative of this function is convex. Okay, so hence it's also a convex optimization problem. So these are the observations we have. So use dual when the number of samples m are significantly less. Okay, relative to the number of features. Otherwise, use primal. So if the memory is a constraint, then you may think like this. Now, strong duality and K conditions. Hello.
Hello, sir. Can we assure that primal is always convex?
No, primal is not always convex, right? In this case, it turns out to be convex. Okay. Because yeah, as I explained, right, this is quality, this is convex, and this is convex, right? So let us see what KKT conditions for SVM. Okay.
Yes, then it's better to use dual always, right? Because it can assure convexity, but primal can't assure it.
Yeah, that's fine. Yeah, so but the problem is dual you may do, but what is the guarantee that dual problem is satisfying the strong duality, and whatever you solve for dual may not be relevant for primal. If there is a duality gap, then you may not hit the primal optimal, right? So dual can be used, and also there could be constraint based on whether your M is very big or not. Okay. So even though the original problem is non-linear, maybe I'm happy.
Do you mean,
Yes.
so do you mean that in some cases dual and primal give different answers?
Yeah, that's what we discussed in the last class, right? So there is a strong duality, right? So if you have maintained strong duality only, then so you have a P star primal optimal and you have a D star is dual optimal. I'm solving dual, then I may stop here because they don't satisfy the strong duality. So then our main objective was to solve for the primal, but I solved via the dual, so I will only end up here. I'm still this far from the primal. Your goal is to provide solution to the primal, right? Okay.
Yeah, yes, sir.
Okay, so then we are talking about strong duality here. So the question is, in the SVM case, does it satisfy strong duality in the formulations that we have discussed? So if you see, this is not the exact slide number anymore, but Slater condition, if you recall, if Slater condition when your inequality constraints were linear, right? So what was the condition for the linear constraints, right? So it's like, remember, if there is when some fi's are affine, so for affine you don't need to satisfy the strict inequality. If you remember the Slater condition is only worried about if there is a non-affine, then you should have an X for which you have strict inequality for non-affine. Okay, so these are like affine, and these are non-affine. So this is something we did in the previous classes, that if you have affine inequality, then no need to find x for which its strict inequality is needed. Strict inequality is needed for Slater condition only when we have non-affine function, in other words, non-linear. So in this case, we are lucky that there is no non-linear case anyway. So we by default, this condition is satisfied because there is no non-linear fi left. So all are linear, and for linear, less than equal to 0 is allowed by the Slater condition, and non-linear is not there. So I don't even have to check it. So in other words, by default, Slater condition is satisfied. So Slater condition also required convexity. So this convexity is maintained. So overall, now this will satisfy the Slater condition, hence strong duality holds. Okay, because all inequality constraints are affine. Okay, so in that case, they are allowed to be less than equal to. Right, so this is something we did in the previous classes. I hope you recall that. Okay, so strong duality holds here. So in other words, what this is trying to say is that in this problem, it is safe to solve your original problem via the dual problem, and you are not going to lose out. Okay, so in this case, the D star and P star are the same. Okay, so I can solve via this. I can solve via this. I'm guaranteed that I will reach also the primal optimal, which is the main objective anyway. So solving primal from the dual, assume that the dual problem is solved to obtain the dual optimal lambda star. So once I have obtained, let us say lambda star, we are maximizing over the lambda. So the question is, how do I get back the x star, which is the primal optimal? Well, the first step is that you solve the dual. That gives you lambda star. Now you set the derivative of L, which is the Lagrangian, with respect to W and equate it to 0. Okay, and then if we do that, then we have this. This is something we have seen. Hence, we get the primal optimal W star by substituting lambda I. Wherever we have lambda I star, I will just put I will just put lambda star. Okay, and okay, sorry. So the W was our primal optimal primal variable, right? So W star is something we are supposed to find, right? So that we can do, and Xi's are your samples data. So you just substitute those sample data, and then Yi is the corresponding level, and then lambda star is the one that you optimal solution of this, and that's how you get the W star. Okay, the intercept B star is a little bit interesting because the way it is done is shown here, like why the optimal intercept is this. The whole idea here is to find the optimal intercept B star. What is B? B is something that is at equal distance from here and here, right? So you take a projection of W star. Okay, so W star you found, right? Now the question is, you take the projections and then see which one which point is the closest by doing these projections, and take the shortest. Okay, so one case will be like the minimum. Okay, minimum least farthest. So I will find out the least farthest. In other words, like I'm looking for that support vector. So that will give me that support vector. Okay, if you have a hand of support vector, obviously you can put that directly. So that will give me this. And then since W is this way, if I choose a projection, then I have to maximize, in other words, okay, because the W star will be like minus W star now, right? And then I will also take projections among these guys and check which is at the closest distance. So this will give me this, okay, W star, this one and this one. Okay, so max max for these guys. Okay, -1. Okay, so these are the negative levels 1. We will be taking the max, and then for these guys, we will be taking the mean. Okay, because the W star will be like the negative, because the direction of the normal will be reversed here, right? So this will and then so the distance here, right? And then the distance here, and we have to take like the sum and then divide by 2. What is the midpoint distance between the two, right? Because this tells me this distance, this tells me this distance, and B has to be exactly in the middle, right? So B has to be exactly in the middle. So let us say this distance was C and this distance was D. The B will be C plus D by 2. Okay, so that's the trick being used here. Okay, so the B will be just C plus D by 2. So in this case, the C will be the farthest distance on this side. I mean, not the farthest, like the smallest distance on this side, and smallest distance in the minus W direction side. Okay. Or you can change this to max, because minus of W will become max. Same thing as doing max of W. Okay. So basically what we are doing here is finding C and finding D. Okay, here and here, and then C plus D by 2 is the middle plane. So it looks a little bit jumbled up, but essentially the idea is okay. And so that gives us the optimal intercept B, because we already know that B is in the middle of the two supporting vectors, right? So this is how we can compute the B. Okay, so these things, there will be an assignment where you have to put this. Okay, all this is like known to you. So W star is known to you, and Xi samples are known to you for the +1. So you may try to do this. And another thing is, like, if you already have a hand of the support vector, you can immediately take the supporting vector and don't have to do maximize and minimize. Okay, you can directly have a hand of the supporting vector here, supporting vector, then you know the distance from there. Okay.
Yes, sir, that's what. If we know the support vector, we can just substitute W and get B, right? Yeah,
exactly. So if you know the supporting vector, then it's done, because these guys will be maximized if Xi is the supporting vector, and this guy will be minimized if the Xi on the other side with the level +1 is the supporting vector. Okay, so here I have written in a very general form, but once the supporting vector are known, it's very easy. Okay, so we can extend the SVM using like for noisy data also we can extend SVM. So what we have assumed so far is that the samples that we find are not noisy. Okay, so when they are not noisy, then in our case, what we have found is like this is our separating hyperplane, and this is the supporting hyperplanes, and then we never assumed anything here. The problem with this approach is that in practice the data do happen to be noisy, and in other words, even the supporting vector data may be a noisy data. Okay, so in that case we allow for some relaxation. So our margin is soft now, not hard. In other words, like let us say if you have a cloud of data, so let us say cloud data is there. Okay, and let us say some outliers were here and some points were here, but majority of the points were here for the other class, and for this class the cross most points were here. So this data that you see here seems like a noisy data. I mean, so seems noisy. Okay, so it could happen that in those boundary cases when you did a data collection, which is the case. Okay, it happens that when you do a data collection, you end up creating some noise. So ideally, you knew that they could have been separated, and these were just some outliers. Okay, some here and there they were lying, and so considering these as noise, we should have kind of assumed them there to be not there anyway. Okay, because they were in the sense like they were noise. So how do you do SVM in that case? So you allow for some merge. So you allow your supporting vector to be here and supporting vector to here, and the ones you allow some data that is inside. You don't allow too many. Okay, as I said, like most data are densely populated here, and most data are densely populated here. There is some noise that is here. I'm trying to allow for that, but not too many. Okay, if there were too many, then maybe they were actual data, and maybe they were not linearly separable anyway. Then I will go for kernel method and so on. So to allow for a linearly separable data and to allow for the noise, we want to modify a little bit the SVM, and we call it soft margin. Earlier we were hard margins. In other words, we were very strict that we don't in our model, we don't assume any noise. So we don't allow any noise. So between the two supporting plane, there was no noisy data. Now we are saying we will allow some noisy data between supporting hyperplane. So this is the case that you will see here. The supporting vectors are assumed to be here and assumed to be here, and we have allowed some noisy data to be inside, assuming that that was an error in the data collection. They should not have been there in the first place anyway. Okay, so they are noisy. So the data is noisy and it is not linearly separable for the moment. Okay, so it's not linearly separable because I cannot draw this way, I cannot draw this way. Each time I have one point of the other class. So modify SVM optimization model to allow for noisy data, formulate optimization problem so that noisy data is allowed between the gap. So that's what I said. So let us look into this model now. So we want to allow for noisy data, that is allow some sample xi to be between dotted planes. Okay, so we want to allow that. So instead of asking for, remember the inequality for the strict, the hard margin SVM was xi plus b was strictly greater than equal to 1, right? So our concept of 1 was like this, right? So but what we want now is we want to allow for some penetration between the gap. So this will allow the penetration. So 1 minus ji will be somewhere here and 1 minus ji will be somewhere here. Okay, so this you can think of ji. So I'm allowing for some points to be inside the ji gap. The strict gap was 1. Okay, up to scaling and so on, and then ji is the additional amount I am allowing. So there will be some yi that will satisfy 1 minus ji. So some of these, like these guys, will be allowed now. Okay, so our margin is no longer strict or hard. It is now softened. Okay, also we don't want too many xi to be between the dotted plane. So as I said below, we are allowing for some, but we don't want to allow too many, because in case there are too many, then they are not linearly separable in the first place. Our assumption has been that there are some noisy data that came, and that has to be taken into account. So to not allow too many xi, we will also put a penalty. Remember penalty, what we learned from the previous class? It's a way to play around a little bit with what I want and what I don't want, right? In this case, what I don't want? I don't want too many noisy data inside. Okay, so what I don't want is not too many of these ji. Remember, ji corresponds to xi, right? So ji corresponds to xi. So I don't want So in our case, like JIs we are thinking of, like this is 1 for some sample 0.1, 0.2, 0.6, right? So we don't want too many of this. We don't want too many of this, right? So hence we will put a penalty here. So we don't want too many of these JIs. And then we put a constant here. So this is the penalty constant. Depending on the penalty, we will see how soft or how hard we want to make this. Okay, so if C is 0, then obviously we don't want any like it's a hard margin basically. And as we increase this C, then we are allowing for more and more softness of the margin. Okay, so what will the optimizer do in this case? The optimizer, as I said, depending on your value of C, the optimizer will see, right? Optimizer has two things in mind. It has to minimize this, it has to minimize this term. But moment you put C to be very large, optimizer focus will go more and more on this term. Okay, so if C is like million or whatever, very large value, let us say, relative to this, obviously. So when you are trying to minimize, then optimizer is like an agent. So it tries to see where is the most benefit to minimize. So if this guy is loaded with high penalty constant, then optimizer will benefit a lot by decreasing this. Okay. In other words, the optimizer will try to make it as hard as possible. Okay. Okay. So it will try to minimize this and make it 0. Okay, so in that case, like you are not really allowing like too much. So all the JI will be forced to be 0 in that case if the C is very large. Okay, if the C is very large, then all the JI will be forced to be 0. So there is a like trade-off here. Like if I C equals to 0, then it boils down to, yeah, it's just only this term is left. If C is very high, then it will try to focus more on this. Now let me write down the, so since it is a minimization, the larger values of JI will be discouraged. Okay. And so this is the constraint. Okay. And so constraint is this, and then this is the penalty term we have here. And now we can also write the dual in the same way like we did before, right? So dual is something like I let you just check for this, why the dual is of this form. So you write down the Lagrangian and so on. You will also be forced to have this upper bounded by C. Okay, so I let you like do this, figure this out, why the dual will be this. Okay, so this is what we are we have for the soft margin. This is the primal optimization problem. So for C very large, the soft margin will be equivalent to the hard margin. If C is small, we are allowing for misclassification. Okay, so if C is large, then soft margin is equivalent to hard margin. So C is large. Okay, in this case, the C is large here. And the decision boundary we got is this guy. Okay, so in this case, it's a hard margin. Yeah, and then as you decrease this more and more, I'm allowing more and more misclassification, because if I see here, so here, like how many misclassification I allowed, right? So let's see. C is small, we allow for misclassification. So C is small here. So more are misclassified, right? So more pink are yeah. So more pink are on this side, lesser pink on this side, and lesser pink on this side. So lesser and lesser misclassification is allowed. Okay, so the whole point, remember, was soft margin is a soft margin. More you soften, okay, so the more you are allowing for the misclassification, right? So these are the effect of the various values of the penalty term. Keeping C very high, it means that you want very less to be misclassified. In other words, you are believing that maybe you are believing that maybe the problem does not have any noise. Okay, so that's why you are very harsh on that. And in this case, I'm allowing a little bit. I'm allowing here, and I'm allowing here. So it's like my intuition is that these were really noisy data. So I was not really worried about that. So these were noisy. Again, this is a hyperparameter, so I don't know precisely like this data I'm assuming, right? So I am assuming that these data are noisy, and that's why I'm doing this. But then again, this is a hyperparameter. So if you have no idea, then you have to play with this, and depending on the prediction, whether it makes sense or not, you have to twin it again and again. So yeah, so C is something one has to play with, and during the testing time, you have to make sense of whether you trained your model well by choosing certain value of the C. Okay. Okay. So soft margin primal is this form, and the dual is this form. Additional advantages of primal over the dual. So we see xi dot xj in the dual. Can we make use of this term? I believe I'm talking about dual over primal. Okay, so what are there any additional advantages of dual over the primal? What are the advantages of dual over the primal, right? We see some term here, right? Xi, xj in the dual, right? So can we make use of this term? Right? Can we make use of this term? This is like sample I transpose sample j, right? So that's when things are interesting, because we can make use of this in kernel method. So sample xi also appears in the constraint in the primal. Is that useful? So the fact that xi, xj appears only in the dual objective, and that too as a dot product, is very useful. Let us see how. So this allows the mapping of the samples to a space where they may be linearly separated. Okay, right now it may not make sense why the appearance of this is interesting. That leads to something called kernel trick that we will see. Okay. Okay, so let me proceed before I answer this question. So remember, in the beginning of the SVM, we talked about also some nonlinear data like this. In this case, we cannot hope to find a hyperplane and then supporting hyperplane and do the separation. That's not possible because this is not linearly separable. So how do we use SVM in such case? Then we apply something called kernel. We push other label data up, and then the other one keep it at the same plane or maybe push down. And then if that is the case, by assuming the higher dimensional space, and then you can separate it by a hyperplane. So that's the basic idea here. So on the left, the data is not linearly separable in the input space. So that's our input space. So we want to do a transformation in some output space where it is indeed separable. So in this picture, that's what we saw. So how to find such map phi that will do something like this, right? Okay, so let us look into the data. in the input space. So how the data looks like in the input space? Well, this is how it looks like. And how it will look like in the output space, it will look like this. Okay, this is basically the prediction function here, right? So it is sine of w dot phi x. So assuming that like I have transformed x to the new feature space phi x, then in that case, this is how the data will look like in the after mapping to the feature, right? Okay, so wherever I have x, they are mapped by phi. So, and in this case, what do? We solve for the dual problem for alpha I, compute WB from above, and then predict fx above. In this case, solve alpha I using dual and compute WB. Compute WB, yeah, again, and then predict with fx. Okay, so what are the advantages we have? Okay, so let us see what we can do if I do a feature mapping like this. Because I do want to go from non-linearly separable to linearly separable, right? So I do need to use the kernel. So I want to figure out what could be done here, right? So let us substitute W here, okay, and see what can come out. So this is in our new space, right? And this here we are trying to figure out how things look like. So now fx will be sine of alpha I yi. So these were from the w term. So we substituted w here, and then we will have phi xi time dotted with phi x. So phi xi dotted with phi x. Okay, and then the b term is separately there. So if we combine these two terms, then we get so-called kernel. Okay, it's like a matrix. Okay, so k xi x term will be xi x. Okay, so this is like a, yeah, some, or you can think of this as some operator that does this vector dotted with vector operation. I mean, if I vary I, then I will get the other entries, right? But right now this is just some number. Okay, if I vary both x and xi, then obviously, but for the moment, yes, just to correct myself, this is a dot product of two vector. So this will, for the moment, this is just a number. Okay. Okay. Now the question is, what do I gain by this, right? So what did I do? Initially, our model was like this, and later we said that we did a feature mapping by phi, and we got this. And then in this case, our fx function looks like this. Now the point is, what is the benefit of doing all this? So what we know is, like, we don't need to know the phi explicitly. It is enough to know the output. It is not necessary to know the phi itself, but if somehow I know how to get the dot product, that will be good enough. Okay, so this may sound a little bit strange to you right now, because you will say that without knowing phi, how can I compute the dot product, right? Because the whole point was to take my x to some space where I see x as phi x. Now, without even knowing phi x, right, how can I compute these guys? Right, that looks a very strange thing right now. Like, what am I talking about, right? Like, this, does it make sense? It turns out that it is possible to get directly these k values without even knowing the phi value. Okay, let us see some example on why I claim that. So avoid explicit computation of the feature or infinite length vector. So one of the goal here is to like, even if you know phi, then it may not be a good idea to do dot product in this space. Remember, what is the intuition behind this? The intuition behind this is that usually what is happening is that our x is in 2D. And when we are doing feature, since we want nonlinear separation to be linearly separable, our phi x is going into some higher dimensional space. Let us say R cube, right? That's what we are planning, right? Now, if I do dot products in this space of the things like xi and phi x, both are in R cube. Okay, both are three-dimensional vector. Doing dot product of three-dimensional vector will cost me a lot more, right? Will cost me a lot more. For the moment, that's where I will stop. Stop in the sense like the argument, right? Not the class, but the argument stops here. Like if you can avoid that. Okay, so in other words, and I'm talking about R2, right? You may, if the data is like, let us say multi-class and so on, is highly nonlinear, you may need even higher dimension. Maybe you will need a 10-dimensional space, who knows? If there is a lot of class here to be done, and then so you will need even more higher dimensional space. So computing dot product in a high dimensional space is way too costly now. And for the moment, these are just small examples. So I'm talking about 2 and 3. So no big difference. But technically, it may be from 10 million to 100 million could be the case. So then you have to worry about that. So is it possible that you avoid doing dot product here? Somehow you fall back here. Okay, that looks very strange things to ask for, but let us see how. So a kernel we have seen is a dot product of in some feature space. So that's how we define the kernel. Okay, so we have used this definition already here. So more precisely, we define xi xj to be phi xi phi xj. And there are some kernels, okay, that people use in SVM. So this is the linear kernel where xi dot xj, like very straightforward. You can do something called Gaussian kernel. So this is e to the minus gamma xi minus xj square. You can do exponential kernel where just the square part is missing here. And then you can do some polynomial. So obviously linear is a special case of the polynomial with p equals to 0 and q equals to 1. So here xi dot xj, and then if you take powers, then you will get higher order polynomials. And they have this specific form because of the dot product that we are trying to figure out in this space and not in this space. So even the kernels that you see here are chosen in a specific way that allows me to compute dot products in the original feature space itself. So this also can be seen as a dot product. This is seen as a dot product. Remember, nowhere we are using phi, right? Nowhere we are using phi, right? So the kernel values are being obtained by doing dot products in the original feature space and not in the mapped feature space, which was phi. If it was in the map, then we would do phi xi phi xj. That we are avoiding, right? That's the whole idea. You already got the hint of why we are doing this, and we are defining kernels to be like this. Now the only question is like if we are defining kernels with our own convenience, right, such that we see dot products inside, but will they really help? Are they really good kernel? Right, this one, like, will they really separate our data and so on, right? Okay, so let us see some examples of why those are good kernels for many tasks. So let us say this data, right? So this data is not linearly separable, right? Because no way I can put a hyperplane such that one both the star on the one side and then both the filled circles are on the other side, right? So it is not linearly separable. Data is not linearly separable. Now let us play with the kernel, which is polynomial in our case, right? So polynomial kernel are like this. So this is of this form where p is equal to 0 and q is 2. 0 and q is 2. So this is what we get. So to map the data to high dimensional and to make it linearly separable. So we believe that this kernel will map it to a good space where it will be linearly separable. OK, so since this is a 2D, let us say that this is x1 is like this, x2 z1 is like this. Now let us do this computation, right? So kernel of x dot z is, according to our definition, is x dot z's whole square. And so in other words, x is x1, x2, z1, z2. We took a dot product and then square it. If we do this, then we get this. x1 z1, this is the result of the dot product x2 z2 and then square of that. If we do further expand this square, then we get this term, and now we can write this as a dot product again back as a dot product, and we can identify these as feature phi x and these as feature phi z. Okay, so after mapping x by 5, I get this, and after mapping z by phi, I get this. Okay, so this acts like a phi function that actually I was looking for. So what we are doing here is reverse engineering in some sense. Okay, so our original problem was that I am given some data in non-linearly separable, for example, here, and I want to do this linearly separable, right? So our first step could have been to actually find phi and then see whether it helps or not, right? So, but then these kernels are like templates that one can try, and they do help with nonlinearly separable data. And once I do this, so the kernel, the way they are defined is like they are dot products in the original space. So this dot product computations can be done, but your original kernel mapping was this. Okay, so phi x, so the mapping that was defined was phi x is x1 square by square root of 2 x1 x2 by x2 square. So this is the map actually we are looking for that will allow this to separate. That's what we are hoping. And the main thing was to avoid the dot product, and to avoid the dot product, we have used a certain spatial kernel, but implicitly in the hindsight, there is some feature mapping that can be identified with this kernel. Okay, now the question is like, does this kernel help? Okay, does this kernel help? Or in other words, does this mapping of phi x phi z defined to be like this, does it make it linearly separable? So let us see in this case, it turns out that yes, in the last slide, this is the feature mapping we had. Now let us look into these points, right? So the x1 point is 0, 1. So this point is 0, 1, right? So this point is 0, 1, and then similarly x2 is 0, minus 1. So this point, and so on. Now let us multiply these points by this feature mapping. So if we do this, then let us see what phi does to the x1 vector. So phi does to the x1 vector, right? So x1 is 0, 1, right? So here if you put 0, say 0, and here since x1 is 0, so the first component 0, so this is still 0, and then x2 square, so x2 is 1 here, so this is 1, so it maps to 0, 0, 1. Similarly, you can say that phi x2, so phi x1 is mapping to 0, 0, 1. Okay, so this is like z x1 x2, yeah, I believe this is 0, 0, 1. Okay, so this I am assuming that this is the z vector. Okay, and so x1 and x2 both are mapped to 0, 0, 1, right? Yeah, so both are mapped to 0, 0, 1. So they are coincided here. Okay, so both are here, and x3 and x4 both coincides here. Okay, so these are x3 and x4. Okay, they coincided, that's a different story, but now they are separable. Okay, so now I can put a plane like this and they get separated, right? So after phi transformation, the points are now linearly separable. So that was the thing that I wanted, to do a mapping such that the point this gets separated. Okay, I can apply a usual SVM on this now.
Hello, sir.
So yes.
Hello, sir.
Yes.
Sir, so we actually moved to the new feature space, right?
Yeah.
Then just now you said we won't move to the new feature space.
We want.
Move to the new feature space. We will be working in the same space.
No, we do move, but the point is, if we go back, look here, right? so we do have to move to new space. Why? Because we want to do linearly separable. But if we do that, then we get this model. And in that model, we found that we are supposed to find dot products. To find the dot products, it's not easy, especially if the new feature space is higher dimensional. So we want to do a trick such that the dot product can be computed only from the original space itself. I never said that I don't have to go. I will work only with the original space. No, I said that the dot product will be worked out in the original space. Okay, but the problem has been transformed to the new space.
So you're saying that we don't need phi, only need k.
Yeah, we only need k. So the dot product, which could be potentially troublesome in higher dimension, can it be computed using some dot products in the original feature space itself? So that's the idea here. So let us see. So this is linearly separable, and now, yeah. So this is now linearly separable, and then so this is just an illustration of what happened with when I used this phi mapping, right? But when I have to do actual computations, I will need to do dot products. I will never use phi anyway. Just now I told you why, right? I just need dot products. If the dot products I can compute, and how can I compute the dot products? Well, dot products I will just compute by this, because this guy is the dot product of this. So phi x dot phi z is nothing but x dot z whole square. And x dot z can be computed in the original feature space. So that's why. So this computation is much cheaper than this dot product. If you see here how many flops are needed, so 1, 2, 3, and then square is 4. Okay, here you have a lot more. Okay, so here the cost is almost 4, and in this case it's like 2, and then square root 2 will take one more, so 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so the cost of computation is 4 here, combining the addition and multiplication and square. And this is obviously approximate. You may say that square may be taking more and less, but there is a clear benefit. We already see that 4 is indeed less than 11. So these are the benefits we get by using this so-called kernel trick. Okay, so let us. So here what I'm trying to say is that the feature space might not be unique for the same kernel. So this is just a remark. For instance, if I do phi x1, x2, then this is this. And if I do a dot product of phi x with phi z, I get this. Okay, but I may have started with a different mapping, but I am getting to the same kernel. Okay, so what it is trying to say is that for a kernel, the mappings may be different. Okay, so it may be, same kernel may be arrived at by different mapping. Okay, this is just a property of the kernel. Okay, so now let us see I'm not going into too much of these things. You can play with this thing. Actually, I'm planning to release one assignment so on SVM and recommender, so you can do that. So we can also apply the Gaussian kernel. I have not said anything in detail, but if you do Gaussian kernel, then it will make a bump like this, and then it will put a cavity like this, and then so for one class will be pushed down, another class will be pushed up, and now they will be linearly separable. And and again, the kernel computation in the, if we go back, the Gaussian kernel is this, right? So this again can be computed in the original space, because this is minus gamma xi transpose xi minus xj. Okay, so these are like dot product computations can be done in the original space itself. Okay, by subtracting and then taking the dot product. So this is again cheap. Okay, so now, so this can be done. And yeah, so which kernel with which parameter, these are like hyperparameter. So I'm not going into detail of all this. First of all, it's hyperparameter. So which one to choose, which kernel to choose, and what is the value of C and so on. These are all hyperparameter. You can do cross validation to check which model is suits you. Okay. So so let us go back to the SVM in unconstrained form. And so in unconstrained form, can we put SVM in unconstrained form, right? So the goal here is like, can we remove this constraint somehow? Okay, so we can write the constraint as follows, like this, and we can solve for the ji. Okay, so if we see that ji can be solved like this, ji has a lower bound like this, right? Okay, and then ji's we also know are greater than equal to 0, right? So there are two things, right? Ji greater than equal to 0 and ji is this. So we take a minimum of this, okay, or the maximum of this, right? Yeah, so since it's greater than equal to, so we take the max of either the 0 or the 1 or this guy, right? So this is like, this is f of xi, right? So that's why what I have written shortly here. So ji is max of 0 or 1 minus. So this is 1 minus this guy f xi, yi times yi is also there, f xi, right? So ji can be written like this. In other words, we can remove this constraint and substitute ji to be this. Now the only problem is like is now is that your problem becomes non-differentiable because max is non-differentiable. Max is not differentiable. So you go from a smooth problem to a non-smooth problem, but you get rid of the constraint. So there is a trade-off here. Okay, so if we substitute ji in the objective, if we substitute ji in the objective, then we will have half of w square plus c max this, and this is 1 by 2 c. Okay, what we can do is that since c is a positive, this is equivalent to saying yeah, so what I can do is like I can take c common and then take 1 by c, 1 by 2c norm w square plus summation of the max and so on. Okay, now I know that constant can be removed. Okay, because that doesn't change the optimality. And then we write this in this form, 1 by 2c norm of this, and then 1 by 2c can be taken as lambda. Okay, so here lambda is equal to 1 by 2c. We are just rewriting the things in a clean form, right? So 1 by 2c has been absorbed in lambda, so lambda this, and then yeah, one way to write this is like this. This is another notation of that. So 0, comma 1 minus yi fxi, and plus means like take the maximum of these guys. Okay, so this is just a notation, okay, of this guy. So we can arrive at an unconstrained SVM problem. From a constraint problem, we can get an unconstrained optimization problem, such that we have to like minimize this guy. Okay, minimize over w and v, and this is the whole objective now. So this is the term, this term, and there's lambda omega square is here. So what we did after doing this, what we achieved is that we achieved a unconstrained optimization problem from a constrained optimization problem, and this also works for soft margin because we have this soft margin covered here. Okay, depending on obviously how much softness you want, that depends on C. Okay, so C will decide how much softness we want, and we can also write this in a, and this is the so-called hinge loss. Okay, so this is nothing but hinge loss, and this guy acts like a penalty term here. Okay, so it turns out that SVM can be formulated into wide variety of interesting optimization problems with different types of losses. Okay, so there are variety of loss plus penalty formulations of SVM. One possibility that we just saw is this guy. I can also square this term, like minimizing this would be the same as yeah, so mean squared loss. Yeah, so mean squared loss is like this is the label I have and this is the prediction I have. So I take a difference, square it, and then I also keep the regularization term here. So there are many formulations. I can also choose one norm instead of the two norm. I can choose a combination of the one norm and the two norm. So this is called elastic net, and this is the lasso. And I can also do one norm SVM. So basically the same thing as before, but instead of two norm squared here, you take one norm here. Okay, so this should be two norm. Okay, so there are various names that people have given. Since SVM is popular, they work with different types of different type of loss functions and so on. Okay, so sometimes like some of these are differentiable, some are not, right? For example, if you see these terms, then they are differentiable. But this guy, this is not differentiable. This is differentiable. This is differentiable, but because this is one norm, so this is not differentiable. One norm, so this is not differentiable, and this is also not differentiable. And here also this is not differentiable, but this is differentiable. So one can obtain variety of loss functions and penalty formulations. So this is the modeling part. Okay, which model suits you for which problem, that depends. Okay, but these are the well-known optimization models. So as I said, these are the variety of cases. It's also about convexity or not. So you can also say which one is convex, which one is non-convex, differentiable, and so on. So this is listed here. You can have a look. Okay. So we can also do like a regression, but let me skip this. Okay, so remember the dual soft margin SVM with kernel also. Okay, how does it look like? It looks like this. Okay, and this is the dual form of that, right? So this is the dual derivation of the soft margin with kernel now. Okay, so that's how the form looks like. Okay, and so how does this map to what we know from before, right? So recall the quadratic program. Quadratic program are like this: quadratic objective, affine inequality constraints, and affine equality constraints, right? So the whole point now is, given a new problem, how do you put that into the form that you already know, right? So the first step is to actually model your problem, and then to figure out whether it's linear, non-linear. If non-linear, then apply the kernel trick. Okay, so if you want to do the kernel trick, the kernel trick is the trick where the dot product in the new feature space is in fact computed by dot product using k, which uses the dot product in the original feature space. That is the definition of a kernel trick. Okay, so this is the setup we have. Like, can we recognize? So if we want to use a software library, then what are this p here? What are this x here? What are this q here for you? Once you recognize this, and similarly you see the inequality constraints, how can you put this in this form? And what are these equality constraint here? What is your A? What is your B? How will you assemble all this data? Basically, how will you assemble all this? P, Q, G, H, X is unknown here, but what are the P, Q, G, H, A, B here? Okay, so that's something we need to know, right? So we can use some vectorized notation, right? We are trying to like put this in this form, right? So let us see how we can do step by step. So since we know that this is a maximize in lambda, so unknown has to be yi, sorry, not yi, but lambda I. OK, so let us denote that by x just to match with this guy x. So lambda 1 to lambda m and transpose, and then substitute this by some appropriate kernel. Again, as I said, kernel is hyperparameter. Which one is appropriate for you? You have to play with that. OK, and then what is my matrix P, given that I use the notation K here? So I have put this as K. Now what is the matrix P, right? So P, if I see this guy here, so this is of the form. So this is a summation here, right? So this is a summation here. So it seems like I can write like this: lambda 1, lambda 2, lambda m transpose. And here there is some matrix P. OK, so I don't have to do transpose now. And then this is like lambda 1 to lambda m. OK, in this form I need to write. And what is that P, right? So P is the remaining term. What are those remaining terms? Remaining terms are like yi, yj and kernel xi, xj. OK, so that's the matrix P that I'm looking for. So the P matrix is yi, yj, k kernel of xi, xj. Good. OK, so we have identified what is the inner P thing that goes with it, with this powers of the variable which are greater than equal to 2 because of the dot product. So all those values which goes with the with combined power is 2, right? So that we know now. So P has been identified, X has been identified. Now, in fact, P could be, you may have to observe -½ also now. OK, so you may have to observe -½ also to clean this -½ term that is lying outside. So you can also observe that in P actually. OK, oh no, sorry. So half is already there. So you keep this half anyway. OK, so we don't have to touch that. We don't have to observe half. I think this is OK. Just P should be exactly this. Now Q is a column vector containing -1. Why is that? So Q times X, right? So X in our case is lambda I. So Q could be just ones, right? So Q is ones, and then we are saying it's -1. Why are we? Oh, OK. I think my goal is also to change this into minimize, because maximize will become minimize if I do a. So I think what I'm trying to do is minimize and then minus lambda I, because I'm also changing this. So maximize will be same as minimize of the negative of the objective, right? So this is like +½ and then lambda I, lambda j, yi, yj, phi xi, phi xj. OK, so that's why the Q will be -1s. That will be the appropriate. OK, and then for the equality constraint, what do we need? Equality constraint is here, right? So equality constraint lambda I. So what do you? So this is your X. So the A matrix seems to be a row vector that is like this. And if I multiply row vector with X, I will get lambda I, yi. And B in our case is 0. OK, because because this is 0 here. And inequalities are like this, but it can be split into two inequalities. So lambda I is greater than equal to 0 and lambda I is less than equal to C. This is not in the appropriate form. So this can be, it is not in appropriate form because this is greater than equal to, it has to be made less than equal to 0. So this is our first inequality and this is our second inequality. This is what we had done here. OK, now we can set G as the following. OK, so this G is following the inequality constraint, right? So we are still worried about this. Now this guy corresponds to these inequality constraints. So put them in the form like this. So this is like Gx is less than equal to h, right? So lambda I must be less than equal to 0. So if I multiply G with now lambda, now you will get the inequality, because if I multiply this with lambda 1, lambda 2, lambda m, right? So do you produce this inequality? and sorry, this inequality first. Okay, so this inequality, so H, what will you choose, right? H will be, so this is corresponding to Gx, right? So Gx will be 1 time, so lambda 1, lambda 2, so I believe this will be C, 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 and then these guys will be 0, 0, 0. So if you choose H to be like this, okay, then let us see G times X is less than equal to H1. So G times X is this, right? So the first part is lambda 1 is less than equal to C. That's correct, right? Then second equation will give us lambda 2 is less than equal to H, which is C. So this is also correct. So this way it will do it for the first time inequalities are like less than equal to C, which is what we want. And then the remaining ones are minus of lambda. So this minus again multiplies with this guy. So minus of lambda 1 is less than equal to 0, which is correct, right? This is what we want. And minus lambda 2 is less than equal to 0 and so on. So by doing this, we have also formulated what is G. All this to make sure that we can use some library, right? So G we have figured out, A we have figured out, H we have figured out, B we have figured out. Okay, G is figured out, Q is figured out, P is figured out. Done. So that's according to this original form. Now you can use a existing library to, so H is what I described here. Now one can use the algorithm to solve the dual kernel SVM using a quadratic program. Okay, so compute the kernel in advance. The kernel was, let us say, a polynomial linear kernel. In this case, we are assuming, but you can use any other kernel. So if possible, using, so in the input space, obviously, for the linear kernel, return K. For polynomial of degree D, we will return this. So these are just additional things about what kernel we want to use. The most important thing is that I need to compute the K. For RBF, I need to compute this guy, okay, which is exponential of x minus this whole square and so on. Okay, so depending on the kernel, we can do this. That's not a big deal. Okay, like there are in Python, you just say which kernel you want to use and they will compute the kernel for you. So this K matrix, you have a hand of that. Now you assemble the matrices and vector, like I said before, to solve the quadratic. And you know what was the P like before. You know the Q, you know the G, H, A, B. So you do that and then you pass this to some library, let us say, pass to some solver. Okay, so you can pass to some solver and that can solve things for you. Okay, so that's the, okay, so I think I will stop here. Okay, so we did kernels and then there will be an assignment. So you can, Jupyter Notebook will be shared with you and there will be a few places where you have to fill the answer for this part. Okay, so I think, yeah, so I think I will stop here because the next topic I want to discuss is some more algorithms. Because from algorithm point of view, we have only seen gradient descent, right? But there are other variants of solvers. So the next class, I will try to discuss this. There is a very general way to define to define solvers, so-called steepest descent. And by different choices of norm, you get different solvers, including the Newton solver that requires Hessian. So far, gradient descent method requires only gradient, right? So we will see solver again. We have seen models so far. We have seen two prominent models. One is like recommender system and one is SVM. We have done SVM in full detail, basically. We have covered soft margin, hard margin, kernel. So basically, you know everything about that. And there will be an assignment based on these two, recommender system and SVM. And we will be doing solvers. And after that, we will be doing some more optimization models. Let us say like something from neural networks or recurrent neural networks. So that I will push this to the last class. Okay. So it's important to discuss now solver and then come back to models again later. So that's the plan. Okay. I believe I have 4 class left, I think. Okay. Okay, then. So I will stop here. And if you have doubts, then you can ask.
G part.
Yes.
G parts, G matrix.
Yeah, the G matrix. Let us see. So this is the G matrix, right? So what do you? What is your question here?
Once repeat, how are you calculating G, sir?
Yeah, G has been assembled in the form that it can produce these inequalities, right? So G, if I choose it to be like this, and this is the way I chose looking at these inequalities. Okay, it did not came out of some procedure. It came out of after looking at these inequalities, what would be the suitable choice of G. So I saw that this set of inequalities satisfy lambda I. So what is this is saying is lambda 1 is less than equal to C, lambda 2 is less than equal to C, and these are happening m times, right? So lambda m is less than equal to C. So how can I write this inequalities in this matrix vector form? Okay, like in one
Okay,
shot,
sir.
right? Yeah. So this is like
So
identity times identity times lambda 1, lambda 2, lambda m is less than equal to the vector that contains all C. Okay, so this identity, this part is actually the identity, and this part is negative of the identity. And so this is like the negative of the identity is less than equal to 0. So negative identity times the lambda vector, or in our case is the x vector, is less than equal to 0. So that will produce this guy. So overall G times x will be less than equal to h with this choice of h. Okay. Any more question?